Hello everybody. Today we're going to look at one more skill that we need to know how to do with vectors before we go into motion with 2 dimensions. We just had a test on motion in 1 dimension, that is linear motion, motion along a straight line. And we will now be going into motion with 2 dimensions, but in order to handle some aspects of that, we need another math skill dealing with vectors, and that's vector resolution. So let's see what that is all about, okay? And you might want 3 colors. I'm using blue, red, and green today. So the first thing, it says, what if we have the resultant, and we need to know which 2 particular vectors were added together to give us this resultant? Now remember, we've already learned how to add 2 perpendicular vectors together to get the resultant. So what if we do the reverse? What if we are given a situation where we have the resultant already and its direction, and we would like to know what 2 particular vectors were added together to give us that resultant vector? What if we want to know the horizontal and vertical vectors? Okay, well, there's a couple of terms we need to know. The first one is the term vector resolution. This is the skill, the math process that we use to resolve, hence the term resolution, resolve or break down a given vector into 2 perpendicular components. All right? Now this can be done to any vector. All right? Any vector, a velocity vector, a displacement vector, an acceleration vector, a force vector. Any vector can be broken down into 2 perpendicular components, a horizontal and a vertical. And make sure you understand what the word component means. A component is just a part of something. Like if you have a stereo system at home, a speaker is a component, a part of the system. So a component would just be this vector and this vector. These are components of the resultant, and that's what we're going to learn how to do. Now, the process, in order to resolve a vector into 2 perpendicular components, we have to use basic right triangle trig. Think about it. If we know the hypotenuse and the angle, its direction, then in order to get the leg opposite or the leg adjacent to that angle, we have to use right triangle trig. Okay? Now, let's take a look at what we would do for each one. Okay? Let's take a look. Let's draw a picture here. Let's just look at one. Okay, I'm going to make a little axis here. And we're going to put our given resultant right here. And I'm going to use a force vector today simply because further down it looks like I was using force when I first made this up. So we're going to use a force vector. So here is our resultant force vector. And it is at some angle theta. Notice it is in the first quadrant. That's fine. So this is our positive x. This is our positive y-axis. We're in the first quadrant. Now, how do we draw the components? Simple. Remember, when we learned how to add 2 vectors together that are perpendicular, they have to be placed tip to tail, and the resultant is always drawn tail to tail, tip to tip between the free ends. Same idea here. Those 2 rules have to be satisfied. But what we're going to do is we're going to start at the tail, and we're going to draw horizontally until we're under the tip. And then from that, we're going to go straight up. So it's like you're walking a path. You start here and you want to get over here, but you can't take the straight line because maybe there's something in the way. So you have to go one way, turn, and go the other way. And when you turn, you make a right angle. So this would be the horizontal component of that resultant force, and I'm using H for horizontal, and this would be the vertical component of that resultant force. You might also see them called F sub x for an x component because it's parallel to the x-axis, and F sub y for a y component because, again, it's parallel to the y-axis, okay? But whether you use H for horizontal or V for vertical or X and Y, that's up to you. For right now, I'm going to use H and V. Okay, so that's how we draw it. Now, what if it was in another quadrant? Okay, well, let's look at a different quadrant. Let's look at the third quadrant. What if it's down here? Okay, so here's negative y hat, here's negative x hat. We're in the third quadrant, so let's say it does something like this. Here's our resultant force, and here's the angle below the negative x-axis. So once again, we want to start here and end up here. We're going this way, but there's something in the way. We can't go through it. So we go this way until we're right above the tip. There's our horizontal component. And then from that, we go straight down. And there's the vertical component. And notice our other vector addition rules are still being met. The two perpendicular vectors are tip to tail, and the resultant is tail to tail, tip to tip. Okay? So see, it's not so hard to draw them, is it? Okay. Now, let's think about the math for a moment. I'm going to start with the horizontal component, simply because it says it right there. And I want you to notice that relative to the angle, that horizontal component is the adjacent leg to the angle, isn't it? Adjacent. So we know the hypotenuse, we know the angle, we want the adjacent leg. Now, that means we're going to use the cosine function. Because if you remember, the cosine of any angle is the adjacent leg divided by the hypotenuse. We know the angle, we know the hypotenuse, we want the adjacent leg. In fact, mathematically, what we would do is we would take this, okay, we would take the hypotenuse that we're dividing by and we'd multiply it on the other side so that the adjacent leg would be the hypotenuse times the cosine of the angle, okay? Now, let's apply that to this right here. So the adjacent leg is the horizontal component that we're looking for. The hypotenuse is the resultant force, and then we have the cosine of the angle. And it's always going to be the hypotenuse times the cosine of the angle to get the adjacent leg. And it doesn't matter if you're talking about a force or a displacement or a velocity. Just replace the F with the other appropriate variable. If you want to find the horizontal component of a velocity vector, you would take the resultant velocity and multiply by the cosine of the angle, okay? Now, let's talk about the vertical component. I'm using green for vertical. The vertical component, if you'll notice, is opposite the angle. It's on the other side of the triangle. So it's the opposite leg. And if we know the hypotenuse and we want to find the opposite leg, that requires us to use the sine function, okay? If you remember, the sine, SOHCAHTOA, the sine is the opposite leg divided by the hypotenuse. So if we want to solve for the opposite leg, then we would say, wait a minute, I want to start with opposite. We would say the opposite leg equals the hypotenuse times the sine of the angle. We're dividing by the hypotenuse, so we multiply it on the other side. So you get hypotenuse times the sine of the angle. Now let's take this and apply it to here. We want to find the vertical component. It is opposite the angle, so we're going to say the hypotenuse, which is the resultant force, times the sine of the angle theta. And this little formula is going to be true whether you're talking about velocities or displacements or accelerations. You just change the f to whatever variable, vector variable you're looking at. If it's a displacement, you put d sub v equals d sub r sine theta. If it's a velocity, v sub v equals v sub r sine theta. Okay? It's always going to be the opposite leg equals the hypotenuse times the sine of the angle. In fact, look, there's a pattern here, isn't there? Whichever leg you're looking for, you're always going to say hypotenuse times either the cosine or the sine. What you need to remember is which one uses the cosine and which one uses the sine. Okay? Remember, the horizontal should always use the cosine because it should always be adjacent to the angle, since we always reference angles from the horizontal. They have to be adjacent. That means the vertical will always be the sine. Now let's look at an example, because there's a couple of things I want to talk about. Different situations that you might see, and you need to learn to think about what's actually physically taking place. All right, so in this first example, we have a child who's pulling a wagon load of toys with a rope held at 43 degrees to the ground. So if we look at this, it might look something like this. You've got a little wagon, okay? And, okay, so you've got some toys in there. Here's a little bear, okay? Okay, yeah, a little cute little teddy bear. All right, and she's pulling it with a rope held at an angle of 43 degrees. Actually, I want to use red for that. I want to keep my colors the same, so hang on while I fix that for just a minute. Okay, so she pulls with a rope at 43 degrees to the horizontal. So here is the resultant force that she's using. Okay, and that's relative to the horizontal, theta, right there. Now I want you to think about what you're doing when you pull something along the ground or along the sidewalk or along the floor. When you pull something, you're doing two things at once. You're pulling forward, which is why the object moves forward, but at the same time, you're also pulling upward, aren't you? So there's the two components of the force in that rope, okay? Now, we know the value of the force in the rope, okay? It's 86 newtons according to this. 86 newtons, and we know the angle is, yeah, there it is, 43 degrees. So if we want to get the two components, then the horizontal component is going to be the resultant times the cosine of the angle, and then the vertical component is going to be the resultant times the sine of the angle, just like we said. All right, so now we can plug and chug. So we get the hypotenuse is 86 newtons times the cosine of 43 degrees. Okay, now, guys, let's stop here for just a minute. If you've got your calculator, I want you to stop and check. Is it in degree mode? If it's in radians, you're going to get some weird answers, okay? So always check, because I know some of you go into a math class and they use radians a lot of times, and then you come back in here and you forget that it's in radians. We use degrees. So then on this bottom one right here, we've got 86 newtons, that's the hypotenuse, times the sine of 43 degrees. Okay, now if you stick those into your calculator, let's see what you get. For the horizontal component, you can check it to make sure that you're doing it right. You should get 63 newtons, okay? And the vertical component, you should get about, oh, if we round to two digits like that one, that would be 59 newtons. Okay? So those are the magnitudes of the two components. Now, if we were also talking about directions, according to the picture I drew, I could say to the right. But what if you drew your wagon being pulled the other way? Well, that's fine too. You could just say to the left because that is what your picture would show. The vertical component. Now, in this case, you're pulling. Whenever you pull, you're pulling up. So this one has to be up, without a doubt. There's no other way. When you pull something, you're pulling out and up at the same time. Okay? Now, it's going to be a little different for the next one. Look at this. It says a man pushes a lawnmower across a yard. Now look, he's pushing, not pulling. Pushing is a little bit different from pulling. It really is. Let's take a look. Okay? So, if I draw a little picture here, here's my lawnmower. Okay? Yes, thank you. I know I can draw. All right. Now, we're pushing along the handle. So there's our resultant force. Notice when you push something, there we go. When you push something along the ground, you don't push upward, okay? The lawnmower's not up here in the air. It's down here on the ground. So you're pushing down and forward. So right here, look here. We're going to go this way and that way. And this is the angle relative to the ground. Always measure from the horizontal the angle of the vector. Now, this is the horizontal component. This is the vertical component. And we're all set. We're ready to find the values. Okay? But the thing is, whenever you pull forward and up. When you push forward and down. Get the difference? Okay. Now, let's do the math. The horizontal component is going to be the resultant force times the cosine of the angle, while the vertical component is going to be the resultant, the hypotenuse, times the sine of the angle. Now, what is the hypotenuse? Well, let's take a look. It says right here that the magnitude of the hypotenuse is 610 newtons, and you're holding it at an angle of 35 degrees to the horizontal, or to the ground. There we go. So now all we have to do is plug and chug. So we get 610 newtons times the cosine of 35 degrees. And for the vertical, 610 newtons times the sine of 35 degrees. Not too bad, is it? Okay, so now, if you chuck those into your calculator, and do that before I show you the answer, see if you can get them correctly first yourself. You should be in degree mode, okay? Now, so if you've paused it and done it yourself, and you have your, oops, I didn't realize y'all couldn't see that because I blew it up. Okay, there we go. If you've paused it, and now you've got your answers, did you get 500 newtons for the magnitude of the horizontal force? And if you want to add the direction, for my picture, that would be to the right. That doesn't mean you couldn't push your lawnmower to the left. And the vertical component, you should have gotten 350 newtons. And that would be down. Because when you push down and out. All right? See, this is not so tough, is it? All right, tomorrow we're going to be practicing using some of this math to break down or resolve a number of vectors to get some good practice before we start our two-dimensional motion on Friday, okay? And two-dimensional motion is probably one of the hardest things we do this year. So you guys need to make sure that you're paying close attention over the next week or so as we talk about two-dimensional motion of objects. Motion that's not in a straight line, in other words. Okay. Well, you all have a good evening. I'll talk to you later. Bye-bye.